Hello students, how are you guys doing today? I'm going over lesson 4.15 using graphs and logarithms to solve problems. This is part one, and the next lesson will be part two. Today is Tuesday, the 5th of May, so happy Cinco de Mayo for all of y'all who celebrate. All right, cool. So let's go over what we're going to learn today. So your learning targets, you guys and ladies will learn how to solve exponential equations using logs or by graphing. So we're going to be solving these exponentials using logs or by graphing when they give us a graph. All right, let's get down to our first. Before we go into our first activity, I wanted to review some of the main ideas you guys were supposed to have learned from lesson 4.14, solving exponential equations. So the first thing that I wanted to go over was solving an exponential equation using logs. And these are just examples like the examples that you guys worked on from lesson 4.14. So let's just go over this. In order for you to be able to solve this exponential function, we need to isolate this 10 to the power of x. So if I want to isolate this 10 to the power of x, I need to get rid of this 2. Since the 2 is multiplying times 10 to the power of x, I get rid of multiplication by dividing both sides by 2. Once I do that, my 2's will eliminate, they will divide out, become 1. So I'm left with 10 to the power of x is equal to 800 divided by 2 is 400. Now that you have 10 to the power of x equals to 400, now in order for you to be able to solve this, you need to convert this into a log function. Now, very quickly before I continue with this, quick friendly reminder that when you have a base to a power of x is equal to something, you convert this into a log by writing log, and then the b is your base, the a would be your inside of the log, and then your x would be what your log is equal to. So the conversion for this problem would be log base 10 of 400 is equal to x. And now that you did this, all you now need to do is grab a calculator. You can use your phone, scientific mode. You just press log 400 because on the calculator it's an automatic base of 10, and you get that x is equal to 2.6. Okay, so that'll be your value for x. This example is an example where the log has a base 10. Here we have the second example is a solving an exponential equation with natural logs. Now, natural logs you learned you use when you're using the base e. Okay, and a friendly reminder that e is approximately 2.718. Okay, just like you guys all know that pi is about 3.14, e is about 2.718. Now, in order for us to be able to solve this exponential equation, we need to isolate the e to the power of ex. That means this 10 is multiplying. We get rid of 10 when it's being multiplied by division. So these 10s divide out, becomes 1. So we're left with e to the 3x power is equal to 250 divided by 10, which is equal to 25. Now, what you guys have learned is that whenever you have a base of e, you no longer use log. Now you're going to use natural log. So very quick, just a side note, e to the x power is equal to a will be converted into a natural log by, so it'll become natural log. So in case you guys didn't realize, or in case you haven't really understood, the e is technically the base of the natural log, except that we usually don't put the e there because we always just assume that it's invisible since the natural log and the e go together. So the e is your base, the a would be what's inside of the natural log, and then the exponent would be what it's equal to. So in this case, we will write natural log, with invisible e here, natural log of 25 is equal to 3x. Okay, so now you get this natural log of 25. You put that in the calculator. So natural log of 25 is equal to about 3.22, I rounded up, and that's equal to 3x. And we solve for x by dividing both sides by 3, and we get x is equal to 3.22 divided by 3, and that's 1.07. 1.07. And that is your answer for the second equation. Okay, so if you did not understand yesterday's lesson, or if you didn't quite get to it, this is basically what you should have learned yesterday. All right, so for our first activity, it says a population of cicadas, and cicadas are these little, they look like grasshoppers, is modeled by the function defined by f of w is equal to 250 times e to the power of 0.5 w, where w is the number of weeks since the population was first measured. Now, question number 1 says, explain why solving the equation 500 is equal to 250 times e to the 0.5 w gives the number of weeks it takes for the cicada population to double. Okay, so why does this equation tell us that it gives us the number of weeks for the population to double? I'm going to go ahead and open this up. Write your answer now. All right, good job. So now let's talk about why it doubles. Now, if you notice, this 250 is our initial population. Okay, so this 250 is our initial population. We notice that we have a W, which stands for weeks. So this is saying when W is equal to 0, the initial population of this cicada grasshopper population is going to be 250. Now, notice this equation has a solution where the number of population is now 500. So 250 times 2 is 500. So this equation does match the equation of the number of weeks the population, how long it takes for the population to double, because our initial was 250, and they want us to figure out how many weeks is it going to take for it now to be 500, which is double of the initial amount. Okay, so now based off of what we learned and what we did in the review samples, the question says, how many weeks does it take the cicada population to double? So what you guys, oops, you did not see that. What you guys have to do now, actually I messed up, you guys did see that. Oh well, we'll just answer some more questions later. So what we have to do now, so it takes about 1.4 weeks, and we need to solve this. So we're gonna practice solving this as we solve the other ones. So the first step here is, since we have 250 times e to the power of 0.5 w, we are going to divide both sides by 250 here and here. So once we divide both sides by 250, these 250s divide out. 500 divided by 250 is 2, so I'm going to continue over here. So it's 2 is equal to e to the 0.5 w. Now, I like to write this where the e to the 0.5 w is first, and then the equals to 2 is second. And the reason why I like doing that is because the transition to an exponential to a natural log would be a lot easier. So this is your base, so we're going to write natural log. This is what goes inside with the natural log, and this exponent is what it's equal to, 0.5 w. So if I wanted to find what w equals, I would divide both sides by 0.5. And these 0.5s divide out, so I'm left with w is equal to, and what you need to do is just put this into the calculator. So you're going to put natural log of 2, close parentheses, divided by 0.5, and you get about 1.386, which will round up to 1.4. So that's why the answer is about 1.4. Okay? All right. So now that I did that with you, now you're going to go ahead and answer question number 1 or number 3. It says use graphing technology, but the graph was already provided, to graph y is equal to f of w, which is this function here, and y equals to 100,000, which is this line right here, on the same axis. Explain why we can use the intersection of the two graphs to estimate when the cicada population will reach 100,000. So go ahead and answer that question now. All right. So now that you guys had a chance to do that, the intersection where the 100,000 y equals 100,000 and the f of w graph cross, they cross right here. And if you notice, that intersection point is at 12 weeks. Okay. So that question is saying, explain why we can use that. Well, here's the sample response. The graph representing y equals 100,000 is the horizontal line showing the population that stays at 100,000. The point where the line intersects the graph represents f, shows the moment when the function f has a value of 100,000. So the w coordinate of that point gives us the time in weeks when that happens. So basically it takes about 12 weeks for the population to reach 100,000. That's what this intersection right here means. Okay? All right. So that's our main activity for today's lesson. Now what we're going to do is we're going to do 3 practice problems just so that you can make sure that you guys fully understand today's objective, which is solving these exponentials with graphs and also by solving them with logs. So the first practice problem that you guys are going to work on says the equation P of h is equal to 5,000 times 2 to the power of h, represents the bacteria population as a function of time in hours. So here is the graph of the function P. It says, use the graph to determine when the population will reach 100,000. So go ahead and answer the question, when will the population reach 100,000? Go ahead and answer it now. All right. So now that you guys have an opportunity to write down your answer or select your answer, first I want you guys to notice that the population is in thousands. So this 20 isn't 20. This 20 is actually 20,000. So since they're asking for 100,000, 100,000 would be this guy here. So if I were to draw a straight line all the way across, my intersection with my graph would be that point. And if I were to make the straightest line possible all the way to that point, my approximation would be about between 4 and 5 hours, approximately 4.5. But if you selected either 4.4 is your answer. But if you selected 4.5, 4.6, those are all pretty good explanation as well. So 4.4 would be the exact approximation of where the this equation, which represents the bacteria population, is going to reach 100,000. So question part B says, explain why log base 2 of 20 also tells us when the population will reach 100,000. So where do we get this log base 2 of 20 to equal 100,000? All right, so I'm going to go ahead and make this equation for you. So basically, it says we basically replace the P of h with 100,000. So we say 5,000 times 2 to the power of h is equal to 100,000. Now you're going to practice and solve this problem on your own, just like we did the other ones. So go ahead and select your answer now. All right, cool. So now that you guys had a chance to solve this on your own, let's go ahead and solve it together. Since this 5,000 is multiplying times the 2 to the power of h, we get rid of that 5,000 by dividing 5,000 both sides of our equation. So once we divide both sides of our equation by 5,000, those 5,000s divide out. We're left with 2 to the power of h is equal to 100,000. 100,000 divided by 5,000 is equal to 20. Now, in order for us to be able to solve this exponential function, I need to convert this exponential equation into a log. And one more time, remember that our log, this is our base, this is the inside of the log, and this is what my log is equal to, right? So then we say log base 2 of 20 is equal to h. And if you notice that this log base 2 of 20 is the same log base 2 of 20 that they're asking us. So this is why we're able to rewrite log base 2 of 20 as being the exact same thing as when the population reaches 100,000. Okay? Okay, cool. So let's move on to example number 2. So example number 2 also talks about bacteria. So the growth of a bacteria population is modeled by the equation P of h is equal to 1,000 times e to the power of 0.4h. For each question, explain or show how you know. So since these are all practice problems, you guys are going to work them out on your own, and then we're going to go over it after you select your answer. So part A says, how long does it take for the population to double? Okay, so I'm going to go ahead and give you guys an opportunity to give your answer to this question. Go ahead and put your answer now. All right, cool. So they want the population, or how long does it take the population to double? Well, automatically, this 1,000 is your initial amount. This is the initial, meaning that's how many bacteria were involved since day 0. So double means multiply this times 2. So we want to figure out how long does it take in hours for our population to now be 2,000. So our equation for this would be 1,000 times e to the power of 0.4h, which is just basically this equation here, equals 2,000 because that's when it's doubled. So to solve this, we're going to divide both sides by 1,000. 1,000s divide out. We are left with e to the 0.4 h is equal to 2. And one more time, this is an exponential equation with base e, so this is going to be converted into a natural log. So one more time, the conversion, in case you guys always forget, which is okay, this is your base, this is the inside, and this is what it's equal to. All right, so now we're going to have natural log of 2. Well, remember that the base is e, but it's always invisible, so we don't put it. So base of e of 2 is equal to 0.4h. Okay, I'm going to continue over here. And okay, so now we have natural log of 2 is equal to 0.4h. And since I want to leave h by itself, I'm going to divide both sides by 0.4. So these 0.4s divide, I'm left with h. Okay, now you got to get a calculator, and you're going to put natural log of 2, close the parentheses, divided by 0.4, and your answer is 1.7. I'll just leave it at 1.7. So 1.7 answer is your answer, which basically means that the growth of the bacteria is going to take 1.7 hours for the population to double. Okay, 1.7 hours for the population to double. Hopefully you guys got that one right. Okay, question B says, how long does it take the population to reach 1 million? All right, so I'm going to just go ahead and give you guys a hint that you're replacing the 1 million for the P of H. Now, look at this example. Try doing this one on your own. Go ahead and put your answer now. All right, cool. So now that you had a chance to do that, very similar, we're going to divide by 1,000 both sides of the equation. So the 1,000s divide out. We're left with e to the power of 0.4h is equal to 1 million divided by 1,000 is equal to 1,000. We make our natural log conversion. So natural log of base invisible e of 1,000 is equal to 0.4 h. Remember, this is your base, this is the inside, this is what it equals to, and this is an h. Okay, and now we divide both sides by 0.4, and the 0.4s divide out. We're left with h is equal to, we get a calculator, natural log of 1,000 divided by 0.4, and we get 17 point, I'm going to round that to a 3 because of the 6. So 17.3. Okay, if you did not do this in the calculator, you're not going to be able to see how rounded it is, so make sure you're also following along by putting this in the calculator. It helps. All right, cool. So what this means, that it takes 17.3 hours for the population to reach 1 million bacteria. Okay? All right, so hopefully these example problems are helping you. We have one more example problem, and I threw this one as a funsy problem. It's not really fun. I call it fun because it looks complicated, but it's really not. The only hint I'm going to give you when you're solving this problem is think of this. Think of a problem where you have 2x plus, I don't know, I'm just making this up, 5 is equal to, let's do 15. How would we solve this? We would subtract 5 to both sides, right? The 5's will cancel out, they'll subtract. You're left with 2x is equal to 10. And finally, we divide by 2. And these 2's will divide out, and your answer would be 5, right? So thinking of this, of these steps, go ahead and try solving this problem. I'll give you one hint for the kicks. You have the left side and you have the right side of the equal sign. Go ahead and put your answer to this problem now. Okay, so now that you guys tried solving this, let's go ahead and work it out. So this plus 20, so notice that it says 9 times 10 to the 0.2x minus 2 power plus 20 is equal to 920. So in order for us to solve this 10 to the 0.2x minus 2, think of this as just being the x. That means we first, over here, we got rid of this plus 5 by subtracting 5, so I'm going to get rid of this plus 20 by subtracting 20 to both sides, right? Okay, these 20s subtract. We're left with 9 times 10 to the 0.2x minus 2 power is equal to 920 minus 20 is equal to 900. Now, this 9 is multiplying times the 10, just like this 2 was multiplying times the x. So whenever they're multiplying, we divide. So in this case, I divide by 9 both sides. The 9's divide out. I'm left with 10 to the 0.2x minus 2 power is equal to 100. And now, because this is a 10 and not an e, I'm going to make this into a log. So one more time, the transformation from an exponential to a logarithmic function is that is your base, this is your inside, and this is what it equals to. Okay? So we write log base 10 of 100 is equal to 0.2x minus 2. All right, so now to be able to solve this, we plug log base 10 of 100 in the calculator, and literally the way you do that is you just put log 100 because your calculator already knows that it's base 10. So log 100 is equal to 2 is equal to 0.2x minus 2. We solve for x, so we add 2 to both sides. These 2 subtract out. 2 plus 2 is equal to 4 is equal to 0.2x. And now we divide by 0.2. Oops. We divide by 0.2. These 0.2's divide out, so x is equal to 4 divided by 0.2 is equal to 20. And that is your answer. Hopefully you got it right. All right, so that's basically example problems from this lesson. You are basically done with this review. Your job now is to go to your go to Schoology, work on the cool down. Good luck. I do want to say make sure you're taking notes on everything that we did because the notes will help you on the cool down if you get stuck. And always remember that you guys are awesome. Thank you very much. And hopefully you guys do really well on today's cool down. With that being said, I'm going to go ahead and log out. Stay cool and make sure you do all your work. Take care, everyone.